All right, welcome everyone. My name is Craig Sipes and I am the local District East STEAM coordinator. So happy to be here with you today. Presenting with me today are our fantastic STEAM coaches. I will let them introduce themselves. Erica.
Hi everyone, I'm Erica Lee. I serve the three northern communities of Boyle Heights, El Sereno, East LA, Lincoln Heights. Inyang.
Hi everyone, my name is Inyang Lee and I support the schools in Southgate and Bell Cudahy Maywood.
And Lillian.
Hi everyone, excuse the hat. I have hat hair. It was cold this morning and now I don't want to take it off. But I support the Huntington Park, Walnut Park, and City of Vernon community of schools.
Thank you. So today we're here for the elementary PD series. This is PD number 2 in this series about the ambitious science teaching practices, otherwise known as the teacher moves. Today, we're going to have intro to the ambitious science teaching practices, and we're going to learn about ambitious science teaching practice number 2, which is eliciting student ideas. So let's begin. So, wow, what a start to the new semester. How are you feeling today and why? So in the chat, don't hit return yet, but we're going to ask you to put a number corresponding to the Lego face emotion that you are feeling right now. So go ahead and put that into the chat, and when I give a countdown, then hit enter. I'll give you a second. All right, and we're going to give a countdown. 3, 2, 1, enter. All right, we see 2. Oh, so lots of 2s. Yes, it's hump day. We got lots of 2s. And oh, 9, parent drama. Oh no, so sorry to hear that. 4, yes, these are not easy times. But despite these not being easy times, we are super happy that you're here with us today. We know that it's difficult, and that just means so much more to us that you are putting in the effort and the energy and the mental attention to develop your craft and to become better at teaching science. So we are here to support you in that endeavor. Thank you for being with us here today. So we want to take where you're at, which is doing really good science in your classroom, and take it to the next level. What are we doing today that's going to help us accomplish that? So today we're going to learn more about the ambitious science teaching practices, otherwise known as the ASTPs or the teacher moves. These are the things that teachers do in order to help students learn. We're going to learn about how to make instructional decisions by eliciting all students' thinking and understanding about scientific ideas. And we're going to learn about how to facilitate making a public record of student thinking and ideas. As a matter of online norms, we're going to ask that everyone have their cameras on. Thank you for doing that. We see Monica's camera is on, Marcela's camera is on, and Terry, hey Terry, Terry's camera's on. Good to see you all. Wonderful to see your faces. And we'll ask that you remain muted until we ask for participation. We will have participation at different points in time. And chat when prompted. You've already done that. Thank you very much. And we'll also engage in some cold calling at times. So thank you very much.
Okay, hey everyone. So these are the instructional levers for this school year, and they're identified foci for the local District East. So at the heart of this diagram, you'll notice the student voice. And in today's PD, we will explore how to amplify student voice utilizing the ambitious science teaching practices and tools to build pedagogy, to build precision of pedagogy. So just take a moment and think about, what does student voice look like, sound like, and feel like in science learning? We're going to have another quick waterfall. So please don't hit enter until we do a countdown. Think about what would that look like or feel like, student voice in a science lesson or during science learning. And on the count of 3, 3, 2, 1, enter. Student hypotheses and questions, students sharing ideas. Thank you, Terry. Thank you, Sylvia. Kids talking, asking questions, engaged and exciting, curious, excited. Sharing ideas with their friends and asking questions. And I'm seeing engaged. Students negotiating how something works, why it works. Thank you, Craig. And yay for, oops, that one just went up. For our San Antonio teachers here, yay. Sharing ideas and being engaged. So students being actively engaged, sharing ideas with their classmates and their teacher, whole class or small group could be all examples of student voice. Next slide. So how has NGSS changed teaching and learning of science? The first is that students drive the learning by making sense of an anchoring phenomena or design a solution to a problem. And also NGSS is an integrated three-dimensional learning and assessment where the teacher intentionally selects practice-centered tasks. So by practice-centered, we're talking about the science and engineering practices. And so what is three-dimensional learning and assessment, and how does that play in with NGSS storylines? So the teachers will launch a unit with an anchoring phenomena, something that's going to be intriguing to students, and that's going to be their investigation that they'll be constructing an explanation throughout the course of the unit. So once the anchoring phenomena is launched, the teacher will elicit their initial models and ideas from students through modeling or written explanations. And then plan lessons that that students are engaged in one of several of the science and engineering practices. Then students have an opportunity to revise their initial model and then go by adding on or perhaps changing some of their initial ideas that they've constructed from, that they built upon. And then continue with more lessons, again, more science and engineering practices, and then constructing that final explanation. So the anchoring phenomena can be used as the backbone of the unit to form the storyline where they're going to engage in multiple lessons. So what is NGSS standards-based instruction? When we talk about the 3 dimensions, we start off with what's called the disciplinary core ideas, and you can think about it about what is that students need to know. What are they trying to figure out? Then the science and engineering practices are what students are going to be doing. What is the do? How are students trying to figure it out? And then finally, the lens of a scientist, how are they thinking? Are they looking at specific patterns? Are they looking at cause and effect to help them construct those explanations or even similarities? And of course, it is launched by the anchoring phenomena and the storylines. So this is the why. Why are students trying to figure it out? And as we mentioned, the science and engineering practices, these are the ways that students work to make sense of phenomena. So they may engage in one of several throughout the course of the unit and maybe revisit multiple times depending on their investigations. And these are called the student moves. So in local district east, we've identified 3 higher leverage science and engineering practices. SEP2, developing and using models. 6, constructing explanations, and 7, engaging in argumentation from evidence. And so we see those, the common thread is the claim, evidence, and reasoning. And today we're going to be looking at the teacher moves and how teachers may facilitate students in figuring things out by engaging them through some of those practices. And so, as mentioned, the ambitious science teaching it's a framework for teaching science, and it focuses on equity. And what it does is supports equitable instruction by situating learning in familiar context, being responsive to students' ideas, and knowing that they're going to construct knowledge over time to create those stronger explanations using key ideas and vocabulary. Also demonstrating and encouraging disciplinary conversations, honoring students' sense-making repertoires, and frequently providing opportunities to show understanding. And now, Erica.
So here, we're going to be looking at a second grade class engaging in a phenomenon-driven unit. So as we mentioned, that phenomenon is really going to drive the learning. It's going to help students be engaged to figure out. And in this case, the question that we're going to be asking is, what caused the town of Moncton to flood? We have a few separate segments, and in each of these segments, we're going to ask that you try to see which of these 4 ambitious science teaching practices is the most evident. You might see that some of them kind of intertwine, overlap, but there's going to be one science practice that we're really going to focus on with each segment. I notice we have some familiar faces here, so hopefully if you've seen this already, this is a review, but you can still definitely engage in full participation with us. So to give you a little bit of a background, the DCI here is Earth systems and processes that shape the Earth. The phenomenon is, why did this town of Moncton, which is in Washington, flood after a dam was built on the opposite side of the mountain? The science and engineering practices that we're really going to be looking at here are developing and using models, constructing explanations and designing solutions, and engaging in argumentation from evidence. So as you watch, pay attention to what's happening and take a look and see. All right, so here's that first video.
So we've been investigating the town of Moncton, and we've been wondering and investigating the question, what caused the town of Moncton to flood?
The soil was faster, so the water could go through the glacier moraine to the town of Moncton.
So I heard there's a claim, and I heard some evidence. Can I have someone repeat what you heard? What was the general claim that you heard?
What you see in the video today is young kids weighing multiple hypotheses, checking each other, doing some fact checks, and trying to get to the heart of what part of my statement do you agree or disagree with.
The project that we are working on is really thinking about what certain scientific practices that are central to NGSS look like when working in primary classrooms, so in grades kindergarten through 2nd grade.
What claim did you hear?
I heard that if the glacier left mostly sand and some pebbles in the mountain, then the water would go slower.
Then the water would go slower. Do you agree or disagree?
Agree.
Can you tell me more?
Because when we did the experiment with earth materials and we used sand, it went slower than soil, like pebbles. And I want to add on. Yeah, I want to add on to Jamie's. I agree with it is very compact and it has little tiny spaces in between for the water to go through. But I really think that sand went the slowest because sand has the most littlest things in it.
This video looks at a whole unit of instruction and how teachers can support scientific argumentation inside of modeling at the beginning, middle, and end of a unit.
So to kind of frame our thinking right now, we're going to be guiding you to the first AST, as we call it, Ambitious Science Teaching Practice, which really shows evidence of teaching practice 1. So if you take a look and think about what Dr. Thomas just said, it's how did the teacher plan for engagement with this phenomenon? She was looking at, or the teacher was looking at, what was happening at the beginning, the middle, and the end. And as teachers, we really have to plan for that engagement from the very beginning, have an idea of what my students are going to do throughout this whole unit, and how are they going to really learn and solve what's happening. So it's not something that we just do, at the very beginning and that's it, but it's constantly happening all throughout. So we'll watch the next video clip. And again, let's really look at which of the 4 teaching practices is the most evident. After this segment, we're going to ask that you join a breakout room for a brief discussion about which teaching practice you identified. So try to take a close look.
With drawing our initial models and talking about our own ideas and personal experiences about what we think caused the town to flood. At the beginning of the unit, the students are presented with the phenomena and they're given a model to be thinking about how and why the town had flooded. And so as a teacher, I'm listening to students' ideas, listening to their own language that they're bringing.
His idea was that water was going through the ground, and then there was like a layer of stone up over here, and then the water kept on rising up.
Our model is that maybe the dam exploded because there's such a powerful water current.
Their initial models don't necessarily have a lot of writing, so it's important that you're listening to the students' ideas. Yesterday, you shared your initial ideas of what you think might be happening that's causing the flood for the town of Moncton. And so I have 3 claims that I want to share with you, and I want you to think about them to yourself on whether you agree or whether you would like to make any changes or if you like them just the way they are. So one of the claims we have is, it says, we claim that the water filled up behind the dam and went up the hill and then down to the town. And so I have made copies of the models that showed that idea. Once I had seen those patterns, we presented the claims and asked students to see if they agreed or disagreed with those claims, if they wanted to make any revisions, and had their models where we felt it represented those claims. So she was saying this model should be over here.
Yeah.
Are you agreeing with that? So this model was in the wrong section.
I think there are a few considerations that are important in selecting key claims at the beginning of a unit. That's to anchor modeling and really explaining a phenomenon. The first step that Kitten engaged in was really looking at the range of student models when they first initially thought about what caused the town of Moncton to flood. And so she was trying to select out what are some of the ideas she's seen across models that were common, that were familiar to students, and that also represented a range of perspectives that they'd be able to pursue together over time. Kids come in with a range of really productive and sensible ideas and experiences from their lives. Even young students are coming in with a wealth of experiences, and those are what are particularly generative for supporting their sense making.
Share your idea again, and I want everyone to think about where does this idea go, this personal experience. So hold on, put your hands down, and let's share that story one more time.
So me and Andrew were using those tools, and we pushed the water off the concrete, and so then it soaked inside the soil.
So this is an idea that would agree and support this claim. Okay. We might have some that you would disagree and have some kind of experience that would say that can't happen.
All right, so as we get ready to put you into breakout rooms, really think about which ambitious science teaching practice was the most evident in this video clip. And think about how you know this. Are there some key phrases or words that you heard? Really give evidence for your thinking. So we're gonna put you into breakout rooms.
Okay, we're gonna go ahead and open them up. Lilia, are you able to join your breakout?
I'm sorry, I'm trying to set up my computer. I just got home. I apologize. I'm setting my computer and that way I can transfer from the phone to the computer.
Okay, no
I'm
worries.
coming in. I'm sorry about that.
Okay, okay, we're glad you're here though. Okay, no
Okay,
worries.
sorry. I was listening. I just couldn't. Thank you. Sorry.
Should I put her in the in her breakout room anyway? She can listen.
Sure.
Yeah. Okay.
Thank
so
you.
I'll
Thank
send-
you. I'm listening.
Yeah.
Sorry. I'm trying
Okay.
to
Yeah,
unmute
we'll send you
my-
over to breakout room 1 then.
Do you want to pause recording or do you want to keep going?
All right, welcome back everyone. So we can just unmute, you can type in the chat, which ambitious science teaching practice was the most evident? What keywords, phrases, things that you saw helped you to know? I see we have 2s and 3s, some phrase maybe guiding questions, practice 2 and 3. Okay, how do you know? What did you hear or see that makes you go with 2 or 3? Selecting claims to highlight, preparing charts to help the group ideas. Thank you, Mr. Little. Okay. We definitely see that the teacher had to do a lot of planning. So we know that she had to plan for engagement 1. Here we also see that she is now taking the students' thinking and really highlighting what they were thinking. She's having them discuss their thoughts and ideas. She's asking questions, and that all kind of guides us to really eliciting their ideas. So next slide, please. The teacher is really eliciting students' ideas from those initial models about this puzzling phenomenon, helping or organizing and identifying their initial claims. You saw how she kind of charted out similar ideas and hypotheses. She's valuing their experiences as the evidence to start their agreements and disagreements with the claim. So thank you very much for sharing. We have a next clip. Again, which teacher move, which ambitious science teaching practice is the most evident, and how do you know?
Can we share sound again, please?
So we use the claim T-charts to collect evidence and thinking about the evidence that we are using, whether it proves or disproves that claim. Then as students built their knowledge, they started using other pieces of evidence in the experiments that they've done, the videos that we were watching, the texts that we were reading. And so building that over time, students became more confident in their science ideas. Some students changed their science ideas because of those experiences.
We're going to be shopping for evidence today, and you're going to be thinking about these two claims on whether they help support or disprove these ideas.
They make claims at the beginning of a unit, and then they constantly revise them over time. And they're amounting evidence and weighing evidence throughout the entire unit. But it's all done within the drawing of a scientific model. And they're constantly revisiting and drawing what they can see and what they can't see.
So we're just going to share out in the chat or unmute which teacher move or ambitious science teaching practice did you find was most evident, and how do you know? I see a 4, possibly pressing for evidence-based explanations. I see some 3s, supporting ongoing changes in thinking. Revisiting changing ideas, that's some of our key words that we're hearing. All right. So we definitely see that the teacher does need to engage in all of these practices to some degree. It's something that we see a lot of overlap in. The one that we that we're looking at most specifically here in this video clip is practice 3, supporting ongoing changes in thinking. And what you're really seeing is the students are coming back to go and see how they change their thoughts, what discussions that they can make, that they can have as they are going through those the revision process. We have one more clip. 2 more.
Tell me your claim again.
If the glacier left mostly sand and some rocks in the mountain, then the water would go slower to the town because sand collects the water when the water passes by.
Do you agree with that? So the next step is I want you to be thinking about evidence. We've been talking about evidence. And so how do we know that? So I know this because what I'm hearing you say is that because they're so close together, that it's slowing it down so making it go slower. Is there an example where we saw that because it wasn't so close together that it went faster? Was there a different material that?
Well, I think it was with pebbles.
So we can look to see too, right? Was
The pebble, well, clay was 100.
Did that take longer or shorter amount of time?
Longer.
Yeah.
They're usually modeling and argumentation together. And in that way, these practices co-develop, where they get better at scientific modeling and drawing what they can see and what they can't see, along with developing much richer scientific claims over time.
So again, we're just going to share out which teacher move you might see right there. But you might have noticed that it was going through the cycle, right? So we see that the teacher, or let me ask, what is it that the teacher did then that shows she was pressing for evidence-based explanations? What did we see in the video that shows the teacher was doing ambitious science teaching practice 4? Go ahead and share out, unmute, chat. We see that she referred them to the chart, definitely, right? Asking questions, absolutely. She makes them go look back and say, okay, well, what did you see? Prompted them to look back for data, exactly. And when she does that, yeah, use of the word evidence. When she does that, she has the students tell her and not her kind of restating or saying the answer or whatever they were seeing on their chart. She really makes the children explain what that evidence meant. Thank you for sharing. So we have one last clip here, just kind of as a wrap up to conclude this unit.
We do a lot of thinking about how scientists is not just usually one person, and that is a group of people working together as a community. And so we spend a lot of time at the beginning of the year talking about what does that look like and what does that sound like. It's not quick at all. Yeah, it takes time. So what are you hearing, Jamie?
I
saying?
heard Jamie say that he thought that the sand was going to, I actually can't remember now.
So what can you do?
Can you please repeat it, Jamie?
I agree with Nick's idea because the sand is more packed together than the pebbles. There aren't as many holes in the sand.
Yeah. And I agree with that idea.
I feel like they've changed in having the confidence of being able to share their thinking and agreeing and disagreeing comfortably. I see them now challenging each other and thinking about the ideas that they share and asking really good questions or clarifying what do they mean by that. I want to thank you for sharing and taking a stand today. And we'll continue thinking more, yes, and we'll continue thinking more about what's causing this. So nice job today. Thank you.
So we just love this last clip because you can see the struggle, the actual struggle that our students have in using discussion norms, in remembering what their peers had been saying, and yet there is a community, there's an understanding of how they can use discussion norms and to be able to go back and ask and feel comfortable to ask their peers what they were talking about. So we really want to emphasize the importance of this discourse in science. Scientific argumentation was successful in this classroom because the class was continuously working on those discussion norms to build that community. So discourse is so valuable because it strengthens that achievement in science and literacy. I'm going to pass, oh, no, I have one more slide. So in our next slide, what you'll see is kind of just a cheat sheet, if you will, a placemat of what our ambitious science teaching practices are, 1 through 4, and what they may look like in your classroom. So you'll see that in planning for engagement, you know, you're really connecting to a phenomenon, yeah, that it explains. So it's not just a topic of chemical reactions. We're really looking at, okay, well, why does my bike rust if I leave it out in the rain? Why is it rusting over some time? Instead of just saying, students, we're going to learn about photosynthesis, well, let's learn about how seeds become a tree. These are real life connections that our students can make and that they really become invested in learning about and wanting to find out more about. And as you go through each of these 4 practices, we're going to be listing their ideas in the beginning, the middle, and the end to really think about how and why. That's what we're going to talk about next. And then supporting their ongoing changes in thinking just throughout all of those lessons. And then as you saw in that one of the last clips, they're pressing for evidence-based explanations by referring back to the evidence and the charts. So now I'm going to pass it on to In-Young.
Perhaps we should move to the next slide. Thank you. All right, so for the second portion of this PD, we're going to be looking at the second practice in ambitious science, and that is eliciting students' ideas. And there are 3 parts to this. We'll take a quick look at each one. And we're going to start off with another quick video. Please take a look and think about what you notice and wonder. And can you use scientific reasoning to support an explanation? So what did you notice and what might you be wondering? Please prepare your response in the chat. We're a fairly small group, so please also feel free to unmute and share your voice with the group as well. And let's see what's on your mind. Noticing super high speeds. Wouldn't this be nice when we're driving home from work in traffic? Super fast. That the speed is changing rapidly. Oh, so Ms. Carrillo noticed the path in addition to the train. Yeah, the track or the path is something to notice as well. Is this an Elon Musk invention? I do feel the duty to say, no, it is not. This is actually in Japan at the moment. Sleek shape. Yes. Thank you for these noticings and wonderings. If you have other thoughts in mind, please feel free to continue to drop them in the chat as we go along. The reason why we asked you to think about what you notice and wonder is because it ties into a quick activity we're going to ask you to participate in. Next slide, please. Is it real? Yes, it is real. This is a prototype currently in Japan, but it will be available to the public there in the year 2027. So what you just engage in is what we would invite students to do. We present a phenomenon and we ask them, what do you notice? What do you wonder? But we can also go a step further. Besides just asking them to talk about it or to chat about it, we can give them an opportunity to model. We can invite them to show what they think. So what you're looking at is one type of modeling template. And this is broken up into 3 phases. So they can really dissect this event to before, during, and after. And that means that they're really taking a look at what happens in the entire event, and they're challenging themselves to think of an explanation for the process. If you could please go to the next slide, we'll look at a simplified version of this template. If you'd like to take a closer look, the PDF of this template is in the chat, but we can invite students, especially our primary learners, to think about just one part. What did you notice when you watched that video about the floating train and how it works? And we would invite them to not only draw what they saw, but think about what was unseen or unobservable. We would invite them to draw, and we would point out scientists label their thinking with words as well. Next slide, please. So if time permitted, or if we were together in person, we would invite you to use this modeling template to take a shot. But please think about what you would have put on the model and think about how, if you knew a little bit more, how that model might differ. So our main objective in teaching science is to support changes in students' thinking over time, meaning that that initial invitation to model would be our way of inviting students to have a record of their thinking at the beginning of the unit so that they could reference it as their thinking changes. So this second practice of AST, eliciting students' ideas, gives us a chance to make their thinking visible, and it helps us to make our own teaching decisions based on what we see. We would be able to pivot or adjust our instruction according to the ideas that we elicit. Next slide. So we have another quick breakout activity for you to engage in, and this one is looking at real students' initial models. So A, B, and C, these are 3 models that may represent the various groups of students you may have. And we'll ask you to look at them with the lens of how you would look for possible hypotheses and how you might group them by similarities and differences. So when you go to your breakout rooms, we'll be sharing this screen for you to look at. We know the images might be a little difficult to see, so you can use your controls at the top to zoom in if you'd like. think about what similarities and differences do you notice among these initial models, and what possible hypotheses can you draw from these students' initial models. We'll meet for about 3 to 4 minutes.
Okay, opening all the rooms now.
Ms. Franco, may we help you find your breakout room? Or have you not
Says the
been
host
assigned?
has open breakout rooms. Please wait to be assigned.
Okay, you may have popped in and out while these rooms were made.
Mhm.
Let's see.
Placer, I'm in room 3.
I was in 5.
Yeah,
room
5 would be
okay.
great.
Okay, perfect. There you go.
Thank you, Ms.
Thank
Franco.
Oops, sorry, Inyoung.
That's okay. They probably didn't notice.
I was, oops, I'll pause the recording.
Don't forget to.
All right, welcome back. Sorry for the brief interruption to the images. Hopefully you were able to get a glimpse of the similarities and differences. Please share in the chat. What are some similarities or differences that you saw? You can also unmute and share with the group aloud. You may also want to share some possible hypotheses you as a teacher could gather from these initial models.
We noticed that all the students had mentioned something about magnets.
Mm-hmm.
And one student is really into captioning and really putting their thoughts out on paper, whereas the others are more just beginning that process.
Thank you for sharing aloud. Appreciate your contribution. So there is a common understanding of magnets, while some seem to have elaborated more than others on that, right? A and C, in addition to magnets, also included fire in the models. So there's something to look at there. All right, appreciate your thoughts. Thank you. So the thing is that these models can really help us see the depth of their understanding. So some of these models are clearly showing what is happening, meaning that they were focusing on the visible aspects of that video. But some have gone a step further into explaining the how of the train floating and being able to move so quickly. And some models here, they might even include the why, meaning they might be able to identify certain scientific principles they know are at play to make this train fundamentally work the way that it does. And knowing this about our students can really help us adjust our instruction, right? Because we might then realize that we may need to review certain foundational ideas, or maybe we can move ahead and reinforce with more in-depth activities, something that they are just on the cusp of understanding. Next slide, please. So we labeled those 3 models as being representative of what, how, or why. And modeling is so accessible because even if students might not be able to explain how or why yet, they can all observe and show what they saw. So if students are hesitant or a little unsure of modeling, first of all, we know that modeling and figuring something out in science is going to change. This is a practice that they engage in multiple times throughout a unit, and therefore we really emphasize revising. But at the beginning, we want them to at least be able to show what they saw, to feel confident that they can share observations. Craig is sharing in the chat that modeling is an activity that really allows for a low floor and high ceiling. You can really access a range of students thinking and be able to see that their models make their thinking visible. And then their partial understandings can include connections to alternative conceptions. They might include everyday language and experiences in their labeling, even if it's not academic language yet. They might have self-generated analogies that they tie into this. So then what do we do with these initial models? Next slide, please. We can conduct a gallery walk because we don't want the models to just be for us, the teacher. The audience is everyone. So models make everyone's thinking visible and publicly available to the group. So students can circulate around the room and look at either each individual's or each small group's model. They can travel with a partner so that they have someone to talk with about what they see. And the goal here is to really look, just like we did in our breakout, the lens of what are other people thinking here and what are some things that are the same across some of the models. You might invite them to annotate the range of modeling that they see with colored Post-its. They might travel with some red and green ones, using red ones to know, oh, this is a new idea, maybe something different than what I saw. Or, hey, this one looks kind of like mine. You and I must be thinking the same thing. I'm going to note that with the green Post-it. We're helping our students engage in that practice of really accessing everyone's thinking as public resources. So the gallery walk is just one way of doing that. We could invite students to model in small groups and then go into the gallery walks. We could instead invite them to create a whole class consensus model with us, the teacher. Or and although this one doesn't really tap into modeling as much, we could even start with generating a class list, a whole class list of hypotheses. The teacher could also use the models in this way. Drawing possible hypotheses from students' initial models could really validate their thinking in front of each other, their peers. So we might be able to group like models together and show certain claims that can be revisited throughout a unit. You saw that in the Moncton or the video series we saw about the second grade changing landforms. So here, we saw that there are some students who really understand the magnetic principles, magnetic force principles behind the floating train. But others, they might be thinking about rockets creating the pressure that pushes the train up. Whereas yet another group of students, they might think that the upward force is caused by air. These hypotheses can be charted for the whole class and revisited as they gather more evidence. And of course, all of this is so that we as teachers can adapt further instruction. We can use what they currently know to help generate initial claims, help students really have the confidence to take a stand about what they think is going on, and use that to engage in claim evidence reasoning cycles. We understand that not everyone may have the same understanding, but we treat all their partial understandings as resources. And here we're going to pass to Craig.
So we wanted to leave you in the couple minutes that we have left. We wanted to leave you with a planning tool. And this planning tool, the intention is for you to think and plan ahead as to how you're going to engage students in eliciting their ideas. And then what do you do after you do that? So you can see in the first column, Well, so across this document, I think the link is the link in the chat. Okay, the link to this document's in the chat. There's a PDF version, and then there's also a fillable version. So in this first column, well, let me go across here. So there's step 1, step 2, step 3, step 4. So introducing the puzzling event. What are some generic questions that you might ask? What questions might you specifically pose based upon whatever puzzling event you're going to be presenting? Are there some specific questions and talk strategies that you might use? Here's some things that you might listen for and plan to respond to from your students. And then after you teach it, here's a space for you to type in what you saw your students or what you heard your students say, and then what discourse strategies did you use? This is a reflection column here. If we had time, we would give you an opportunity to put this little piece to practice by looking at a video, but we don't have time today, so we're going to move on to the next part. Page 2 of that then is, page 2 of that same document is then how do we start to think about students' partial understandings, alternative understandings? How can we think about leveraging everyday language that students are using and experiences that they've had? How can those be leverages? So this planning tool is really helpful to think through how you might do that. Unfortunately, we've come to the end of our time here today, so I'm going to let you take this practice tool and take it with you to try on your own. We're not going to have time to do this as a group, unfortunately. On behalf of our team, I want to say thank you for your participation today once again. The evaluation link is in the chat. There's additionally a sign out link. And then there's also a link to the slide deck. So we want to make sure that that you're taking with you this tool, and we want to see you try it out. We want to hear about how that works next time that we meet for session 3. So think about an opportunity where that's coming up in your science planning. Think about, what is this puzzling activity that I've got coming up? What questions can I ask, and how do I take students to step 2 with eliciting hypotheses, and then pressing for possible explanations, and then summarizing and selecting the forms of idea to make them public. So we're looking forward to hearing from you about that for next time. Thank you all once again. And if you have any questions, please don't hesitate to reach out to us. On that note, we're going to say thank you and have a great evening. If you would like to stick by to ask some questions, we'd be happy to interact with you and your questions.